Testing. All right. We're good to go. Okay. So you had a chance to look at the review document and see if you got any really aching, nagging problems that we need to get to before I just start rambling on. I do tend to give you a lot of problems, don't I? 145. Gee.
There's a few.
Maybe a little.
Lots of repetition. I don't know. I've ever told this class in chemistry, if you're not bored stiff working chemistry problems, you're not working enough of them.
Yeah.
Yeah. Okay. Just want to be sure I get that across. Anything in particular, Father?
Some of the problems working with the null method.
Yeah.
Okay. We'll cut straight to the chase. Huh? Let's see which ones that would be over. So we're looking for molar mass. That's what Dumas method does. Let's see. Might be easier for me to find if I look at my worked problems. 139, huh? Yeah. 139 looks like it. Let's see. No, that's what's the density of gas. That's not Dumas. Okay, let's try that again. I'm scanning the answers for grams per mole. Here's one. So that's using Graham's law to do the same thing.
Is it 138?
No, that's Graham's law.
Oh, okay.
Yeah. Dumas is a little simpler, actually. We can get to that one. That's no problem.
Yeah, we'll mark that one too.
Yeah.
Well, I'd like to do one that's in here, rather than just make something up on the fly. What's 77?
Where you need a molecular formula for the compound.
Boron and hydrogen occupies. Okay. Okay. Yeah. This is kind of like the Dumas method. It's sort of a detective. It's giving you choices here. 77 is giving you choices. And the way to tell which one's which is determine the molar mass and then compare it to the molar masses of these choices. Okay, so that's kind of like the Dumas. Okay, so let's do it anyhow, whether it is or not. Okay, so what are we given? 1 gram sample of a gaseous compound. So the mass equals 1 gram. And the composition is made of boron and hydrogen. So we've got boron of a certain amount and hydrogen of a certain amount. The volume of the gas is 0.820 liters, and the pressure is 1 atmosphere, and temperature is 3 degrees centigrade. But we know with gases it's going to have to be Kelvin, right? So we might as well go ahead and change it. That's 280. Okay. what could be the molecular formula for the compound? All right. So as long as we know that our target is the molar mass, we don't have to do the molar masses of these guys yet. We could just determine the molar mass of that. So what do we need to find molar mass, or abbreviated molecular weight? We need mass per mole, right? So we need to know the mass. We have the mass of the gas. Now we can find out how many moles are there. So let's see if we've got enough. What type of function is this? I mean, is this a before, after, or a state function? Do we know before and after in this case? No, we're not given a before and then a change. We're given what is it right now. So that formula is this one, the universal gas equation. So let's see if we've got everything we need. Pressure, volume, temperature, constant, and no moles. We got what we need. So let's solve it for moles. PV over RT. This needs to be, since this is liter atmospheres per mole K, we need pressure in atmospheres. We need volume in liters. Okay. R value, 0.08206. Liter atmospheres per mole K. And then temperature, 280. Now we just need to find out how many moles that is. So 0.820, 0.08206, divided by 280. So I get 3.569 times 10 to the minus 2 moles. And then molecular weight would be grams per mole. Let's just inverse that number. I get 208 grams per mole. Okay. Now we can compare that to our choices. So what are our choices? Let's see, here we go. So A, oops, keep right over there. Let's do it over here. Keep it on screen. First choice, boron trihydride. Okay, so we need to add boron or 3 hydrogens. Let's see, what's boron? 10.81. Yep, 10.81 for boron. Since they're all boron hydrogens, say 10.81 hydrogen 1.01. Because we'll need it again. Okay, so the total for this one would be one of these and 3 hydrogens. So that's 13.84 grams per mole. I don't think it's anywhere near that, do we? How about this one? What's B? B2H6. You know, I think I made a mistake in calculation here. Let me do that again. I did. 28. You probably already saw that, didn't you? You just weren't going to say anything. Okay, so what's this one? Well, 10.81 twice and 6 hydrogens. What did I do wrong? I did something wrong. Let me try it again. Times 2. There we go. 27.7. Okay. That's pretty close. It's a good candidate. Let's see if we got any others that. Well, okay, what are our other choices? Yeah, because we got B4, H10. So that's going to be 40 plus something. That's way too high. B3, H12. So 3 times that's 30. Already it's too high. So we know that's not it. And this is ridiculous. Right? So none of these come even close. That's your best answer. Okay. Now, that could have been derived from the Dumas method. It didn't go into the hairy details of the Dumas method. It just gave us the data to work with. But the process is the same, right? When you go in the lab, you're going to get a weight for your gas, and you're going to get all these conditions surrounding the gas to determine how many moles there are, and then you do the same calculation. All right. Let's see. Do we want to 78? Okay. 78. Man, I can see it. It's starting to get kind of weak here. Okay, so what are we given? A mixture of KCl and KClO3. KCl and KClO3 weighing 1.34 grams. So both together, the mass is equal to 1.34 grams. Those two together. The dry oxygen generated from this reaction, so one of the products of this is oxygen gas. And you keep those together and you get oxygen gas. And it occupies 143 milliliters at STP, standard temperature and pressure. Right? So this is volume, which is equal to 0.143 liters. We're probably going to need it that way anyhow. Standard temperature is, for gases, is 0 degrees. That's 273 K. And pressure standard is 1 atmosphere. Okay. What percent of the original mixture was KClO3? Okay. So the stoichiometry of this reaction is based on that compound, because heating this produces nothing, right? So whatever moles of this will tell us how many moles of that. So, and the reaction that we're talking about here is 2 KClO3 solid yields 2 KCl plus 3O2. Okay. So to answer the question, which was what percentage of this is the original? So we want to know percent composition. We want to know percent KClO3. That's the question. All right. So what we have the total amount here. So we need that amount. And so we got to work backwards to find out how much of that there was originally. Then we could ratio them and got the answer. Okay. So this is basically a stoichiometry problem to begin with. What we have to do is find out, with this information, can we tell how much oxygen there was produced? Well, state function, right? Right. So we got temperature, volume, pressure, constant. We can find moles. So the moles of oxygen produced then is like the one before it, PV over RT. So the pressure is 1 atmosphere because it's standard. The volume is 0.143 liters. Hey, come in, come in. Come in, sign in. R value, 0.08206. Temperature, 273. Okay. So let's see how many moles of oxygen we had. It's 6.383 times 10 to the minus 3 moles of oxygen. Okay? So now that we know how many moles of oxygen were produced, we can find out how many moles of potassium chlorate was there to produce it. 6.383 times 10 moles oxygen. Convert that to 3. And the ratio is 3 oxygens for every 2 potassium chlorates. I'm going to have to switch. Fading too much. Calculator. So I get 4.256 times 10 to the minus 3 moles of potassium chlorate. Okay. So you know how many moles you got. It's easy to figure out how many grams, right? You just need molar mass. So we got to calculate molar mass for potassium chloride. Let's see, potassium is 39. Can't see that far. Where's my periodic table? Here we go. Potassium, 39.10, rounded off. Chlorine is 35.45, I think. And then we have 3 oxygens. So 16, 3 times. So I get 122.55. Multiply that times this, and that gives us the mass of potassium chloride. I get 0.522 grams. And the percentage then would be 0.522 divided by 1.34 times 100. Okay, 38.9. Does that come anywhere close?
Yeah.
Okay. I'm gonna walk through the copy. Okay. Now, of course, that assumes that the conversion was 100%. We're not taking into account efficiency. Or percent yield, as we've called it. All right. Anything else while I'm perusing? What about these ones that are combining moles, molar mass, gas laws, and density? They give you any trouble?
What number?
Like 57, maybe? Oh, while we're in the vicinity, what about 56? Interpreting graphs. Did you have a chance to take a look at that one? Let's see, 56. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? So what does that mean? Which of the following is pressure versus molar mass? So move on. Each is a 1 gram sample. If we plot pressure versus molecular weight, which one looks like that? So that means Now, that's not real clear what it means, is it? Okay. So if you got a 1 gram sample of these different gases, all these different gases, and they have different molecular weights, then you're going to have different numbers of moles of each one. So that means the numbers of moles plotted against pressure. What does that sound like? Well, it actually doesn't sound like anybody's law. It's more like it's derived from the combined gas law. Well, just for argument's sake, the constant. So here's Boyle's, here's Charles, here's Avogadro's. But you can also extract another one out. If you keep the volume and temperature constant, then as the number of moles increases, the pressure increases. So as the number of moles increase, the pressure increases, which would be plotted like this. As the moles increase, pressure increases. But if we hold the mass constant, right, for each of these gases, then as the number of moles increases, the molecular weight would have to decrease, right, because they're inversely proportional. If you hold the mass constant, and let's look at it this way. Molecular weight is grams per mole, right? So if that's held, let's see, if this is constant, and this is molecular weight. So let's do it this way. This is going to be constant, 1 gram. Now we got molecular weight times moles. There we go. So if we hold this constant for all the gases, then if we increase the number of moles like this to get more pressure, the molecular weight is going to go down. So this would be these are directly proportional. These would be inversely proportional, right? Because the product equal to constant is an inverse proportion. So what you're actually going to see here is like that. And that's not one of them. The closest we could get is maybe D. But D's not even right? Because what did we learn from Boyle's law? Pressure times volume is a constant. That produces a hyperbola. Doesn't matter if it's pressure, volume, it could be any 2 variables equal a constant. It's always a hyperbola. And even if we got a negative slope like this one, like E in our answer, it still wouldn't be the right shape. That's the key. Recognizing that this and this make the same type of graph, a hyperbola. Okay? Did I lose you? Okay. Let's try this again. How about, are you good with this one? Right, derived it from here.
My only point of confusion was where you transitioned from the answer to the question into where you want the hyperbola. Like I'm good for answer number 56.
Oh, where I called it a hyperbola?
Just
Or where I made the comparison?
where you made the comparison.
Okay. It's simply the fact that we could say the form here is a variable times a variable is a constant, always produces a hyperbola. So here we have a variable times a variable equals our constant, 1 gram. That's also variable constant. It's a hyperbola.
Okay.
So it will be none of these.
Right. None of them fit. The only one that comes close is D. But it's not right either because that's a straight line. Okay, I digressed. I think we were headed for 57 wrong. I got sidetracked with pretty pictures. Okay, let's see. 57. What are we given? Let's see, we find 250 milliliters of gas at STP. The volume is 250 milliliters or 0.250 liters. At STP, temperature, 0 degrees. And pressure, 1 atmosphere. Has a mass of 0.7 grams. What's the molar mass? Oh, this is too easy. We've already done one like that, haven't we? Oh, I know what threw me. I'm combining equations. We can do it that way. You can do it step by step. You can find out how many moles you got with this information and then combine it with this to find the molar mass. Or you can combine both equations and do it all in one shot. So if you do it that way, we're operating with PV equals nRT to give us moles. And then using mass, we would get molecular weight equals mass per mole, grams per mole. Okay. So if our end result is molecular weight or molar mass, we want to substitute this one somehow into this one so we can do the whole calculation at once and get the molecular weight. So we've already got the mass, so we just need to find an equivalent expression for moles. So we just say moles equals to PV over RT, and that can substitute right here. Divided by PV over RT. And then the denominator of the denominator is the numerator. Remember that one? That flips. So now we've got M RT over P. P is the molar mass. Just algebra. Are we okay? So then you can just substitute in the values here and do the molecular weight in one calculation. So let's see, the mass was 0.7 grams, R is 0.08206, temperature is 273, pressure is 1 atmosphere, and volume is half a liter, quarter liter. There we go. And then we can just do it. Crunch the numbers. We've done all the thinking already. So I get 62.7 grams per mole. Okay. Now, if you want to, you can just use this one to find out how many moles there are. And then divide them. I was just giving you an alternative method. Okay, step by step, baby steps. This is the kind of thought process I would go through if I were going to do these types of analyses and calculations repetitively. Wanted to put it into an Excel spreadsheet as a formula. I would generate this first, and then I'd have my columns of data, and then I'd have the calculation over here, and just one calculation, I'd put it in like that, and then it'd do the whole thing at once. Okay, 57. Anything else bugging you before we go back over to Graham's law? Let's see.
The one that's the change on 58.
Oh, yeah. Okay.
Yeah, will be fine.
58. I wonder if I put too much thought into that one. That looks like a lot of extra talk. Let me see if I can do it without looking at my cheat sheet. Okay, we're given this reaction. Like ammonia and chlorine gas. Sounds like a fun mixture. Makes nitrogen gas plus hydrogen chloride gas. Okay. You react 5 liters of this one with 5 liters of this one, measured at the same conditions in a closed container. Okay. Calculate the ratio of pressures in the container. The final pressure compared to the initial pressure. Okay, so what we're looking for is, yeah.
I just mentioned that, but I just wanted to tell you that the really clinical smell going
Yeah, we smelled it earlier. I think it's coming up through the shower drain.
I just thought we didn't have anything.
Methane smells like rotten egg. I'll go check it right now. I better look into this. Let me pause. Okay. Get my bearings again here. Okay, we're looking for the ratio of final pressure to initial pressure. That's the question. So, what determines the pressure once we've completed this reaction? Well, the initial pressure is based upon the conditions, the initial conditions of gases. All right, so you got so many liters of this one, you got so many liters of that one. And if you can find out what the pressure is in the beginning, then conduct the reaction. How much gas do you have left over? You might have some of this left over, you'll have some of that. And that will give you also a ratio, an amount of gas to determine pressure. But since they're asking for ratio, the assumption is that they don't have to tell us what the conditions are, because the ratio is going to be proportional no matter what the conditions are. Okay. So the trick is it's the number of liters or the volume of the gases are related to this stoichiometry in terms of moles, right? Let's see. Maybe I did need to go through all this logic. The conditions are also going to be constant have to be constant for volume and temperature. I think. Let me be sure. 5 liters of that, 5 liters of that. In a closed container. The container's closed, then the volume is fixed. You can have this volume of that gas and this volume of that gas. Then the total volume has to be fixed because it says it's closed. Okay, so we know that. Temperature. They're all measured at the same conditions. So the temperature has to be constant too, before and after. Okay. All right. So, what we're saying then is, if we look at the equation for ideal gases, if this one's constant and that one's constant and that one's constant, we can put all of those on one side and put the variables on the other side. So that's equal to a constant. So this ratio will be constant. Okay. So that just says as the pressure increases, the number of moles increase. So if we determine the number of moles, initial, at beginning, and before and after, then that will equate to the pressure. So the ratio of the pressures is also related to the number of moles before and after. So if we say, let's see. These two volumes are equal. And if we say that if the volumes are equal, Avogadro says number of moles varies with volume is a constant. So if the volume stays the same for this one, so do the number of moles. So the number of moles of ammonia equals the number of moles of chlorine gas, because the volumes are equal. Okay, so what does that mean? That means if we let the total number of moles, well, if we let, I don't know if we need to call it X. I guess we can. If the number of moles are equal and they're equal to some value X, then the total moles equals 2X. Right? Because you got twice Some over here, same amount over there, so it's 2x. All right. So now that we know that also that the same number of moles we're starting with here and here, the ratio then is if this is x, number of moles, and this is x number of moles, then how many of these does it take to satisfy this one? Which one is limiting? In that case, all you have to do is say the least amount is limiting, right? So this one is the limiting one, the ammonia. The ammonia is going to run out first. And chlorine is in excess. So if this was the total to begin with, okay? Right. So now we're going to react them. We're going to use up all of that one, but we're going to have some of this one left over. Okay? So in the final situation, we're not going to have any of this left, but we're going to have some of this left. Right? So how much of this are we going to use up? So if X represents the number of moles of ammonia, then the ratio of the two wait, that's not right. We're going to use up all these. No, it's the other way around. We've got that much. How much is going to be required to be used for the ammonia? So we're going to use up all that, and what we got left over is 2/3 of what we started with. So how much chlorine is left over? Well, if we're using up 2/3 of it, then we only have 1/3 of what we started with left over. Okay. So 1/3 X remains of the chlorine gas, and none of the ammonia. None of the ammonia remains. Chlorine, we've got this much left over. So we've got 1/3 of our moles left for chlorine. So how much gas did we produce from there to there? All right, so if we had X over here, then we're going to have half an X over here of nitrogen. It's 1/2 of an X. And 2 to 6 is we're going to have 3 times as much HCl as we started with. So HCl then is going to be 3X. So we got this remaining 1/3, 1/2, and 3. So let's see, that's 2/6, and this is 3/6, 5/6, 3 and 5/6. X is on this side. So the initial was 2X, and the final was 3 and, did I do that right? No, I didn't. 1/3 x. This did run out first, didn't it? So we used up, well, if that's x, then this would be a half an x, wouldn't it? It's saying it's a third of an x. Nope, band. I think I'm making it more complicated than it needs to be, don't you? We start off with that many and that many. They're both the same number. And that's right. The total number of moles to start with is 2x. We determined that this one was the limiting one. So it runs out first. It's all gone. So if it's converted, if this x is converted to that, how much of this do we have? We have half an x, don't we? So this is half an x. This is initial. This is before. Down here. This is after. So after is 0 there. So we convert all of that x into this number of moles, half x of moles. We convert 2 to 3 ratio. So that means this is 1/3 of it. No, x. It's 3x. So now we have 3x of that based on this conversion. Okay. What do we have left over here? Well, we only have 1/3 of this left because it took 2 of them to match that one. So we've only got 1/3 of these left. So what it should be is the number of moles that are left over at the end are 1/3, 1/2, 3. So that's 3 5/6 or 15/6. So I may have done this one wrong. So this is the final number of moles, and the initial number of moles, well, this is the initial beginning moles, is 2x. Okay. And the pressures are ratioed the same way as the moles. So if we put 15/6 over 2, what do we get? Well, 2 comes down here, so it's 15/12. What is that? .25 ratio, and I'm saying it's 1.34. So let me see if I put that one on the test or anything like it.
And the process and all.
Please.
Yeah. That's a brain twister.
Yes.
Let's see. It's there. I bet I looked at it when I was making this up and said, no way. Is it an extra credit thing? No. Okay, we're safe. So let's just consider that a brain tease. Let's try something different, something that's solvable. If we want to get over there to Graham's law, maybe dig into that one a little bit. Let's see, where did it go? Mole fractions. That would be a good one. Oh, let's stop at this one. 94. That one coming through. It's really faint. See if this one's recharged itself. Okay, we've got this contraption. Here, there's a valve in the middle. And initially, we have, this is a 2-liter bulb, and this is a 3-liter bulb. Okay. The gas pressure is 1.8 atmospheres in the 2-liter. And in the 3-liter, it's 3 atmospheres. Okay. We want to know what's the final pressure when the valve is opened. The temperature remains constant. So let's look at it qualitatively first. We've got this small bulb here, this big bulb here. That one has a higher pressure than this one. Which way is the gas going to move? Yeah, it's going to move that way. Okay. So what we're probably going to get is a pressure that's in between these two. Now the question is, how do we solve it? Here's what you do. First, it's 2 steps. Well, actually, it's 3. It's 2 steps, and 1 step has 2 parts. The first part is you assume that that's a vacuum. And what happens if you open it into a vacuum? Right? So we've got a before-after situation with the left-hand side. So we're starting off with an initial pressure of 3 atmospheres and an initial volume of 3 liters. Okay? So the final pressure We don't know. But we do know the final volume. If we consider this a vacuum first, just ignore the other gas for now. So the final volume is the sum of the two, right? 5 liters. Okay, now we have a Boyle's law. PV equals PV. Right? So if we solve for this P, well, let's just do it this way. P1, V1 equals P2, V2. Solve for 2 equals P1, V1 over V2. So we can find the pressure in the entire system attributed to that gas. Okay. So initial pressure, 3 atmospheres. Initial volume, liters. Final volume, 5 liters. All right. So it's 9/5. $1.80. Okay, this is the pressure due to the left-hand gas. Now, let's evacuate this one and turn that one loose and see what it does. Okay, so this one is, let's use P3 and P4. So initially, we have a pressure of 1.8 atmospheres and an initial volume of 2 liters and final pressure unknown and a final volume of 5 liters again. Okay. So if we solve this for, let's see, if we say P3, V3 equals P4, V4, and we're solving for the 4 pressure. Here's our pressure, atmospheres, volume 2 liters, final 5. So that's 9/5 again. I did something wrong. Initial. Let me see if I wrote it up there right. The valve between a 2-liter bulb in which the gas is 1.8 and a 3-liter bulb which has 3 atmospheres. Okay, that's right. What's the final pressure in the 2 bulbs? Okay. So the initial pressure is 3, initial volume is 3, final pressure unknown, final volume is 5. Okay. So P1, V1 equals P2, V2. So P2 we're solving for here. V2 comes underneath. P1, V1, 5. 9/5 is 1.8. Okay. I think the problem is that. Now let's see if it works. Just make this 1, 2, 2. Okay, so initial pressure is 1.8 atmospheres. Initial volume is 2 liters. Final pressure unknown. Final volume 5 liters. Okay. 1, 1, 2, 2. Solve for the 2. 1, 1, 2. That's right. Okay, now let's plug it in. P1 is 1.8. V1 is 2. Final 5. So that's 2 times 1.8 is 3.6. 2 divided by 5. 0.72. So this is the contribution from the right-hand ball. Now that we know what each one of them contributes, we use Dalton's law of partial pressures. Because Dalton says that the total pressure is just the combination of the two. Right? So the total is equal to 1.8 plus 0.72, which is 2.52, right? Atmospheres. Is that one of the answers? C. Okay. So we used Boyle's here and Dalton's here. To get the total. Okay, I got sidetracked again. We were on the way to Graham's law, I think. $95 shouldn't give you any trouble. Right. Mole fraction. Think back to that last problem that gave us so much trouble. Where we equated, actually it was the ratio, where the ratio of moles is proportional to the ratio of pressure. So if you know the pressure of your gases, you know the moles. So for 95, you just ratio the pressure of nitrogen to the whole, and that's the mole fraction. Okay. That one. Let's see. Number 98 would take a considerable amount of time. To solve. There's only one false one in there. Yeah, it says look for the false one. We'll come back to that if we have time. Let's tackle a more specific Graham's law problem. About about 100. At 200 K, the molecules or atoms of an unknown gas have an average velocity equal to that of argon at 400 K. What is X? Okay. So we need to use the root mean square calculation. Remember that one? Do we need to do this one? I mean, I don't want to do one that you're already comfortable with. We'll spend time on other things. Go for it. Okay. Okay. 100. So the temperature, we may not have, yeah, we will have to deal with this. 200 K. The molecules or atoms of an unknown gas. So gas X. They have an average velocity, RMS velocity, equal to the average velocity of argon at 400 K. Okay. So we need to find out what's the average velocity of 400 K and compare it to the average velocities of these others. But we don't have to calculate directly. Okay. Oh, okay. Actually, there are two ways to solve the problem. We can use the formula here. That's 3. Yeah. So the root mean square velocity is going to be this temperature times the R value that has joules in it, 8.3145, I believe. And then the molar mass of the gas. And calculate the velocities for each one. The way I did it in here was I solved for, let's see, I did solve for the root mean square velocity for argon there. Okay. Oh, that makes sense. Oh, yeah. That's good. So this value is going to give us something. I need more room than that. Come down here. So this is for argon. At 400 K. Divided by its molar mass. $39.95. Okay. So actually, this is argon right here. The one we're looking for is this one. At 200 K. With an unknown molecular weight. Okay, because it says the root mean square velocity of this unknown gas is the same as argon at this temperature, only it's at this temperature, right? So this root mean square velocity is the same for unknown gas as it is for argon. So now we set them up equal to each other. We just solve for molecular weight or molar mass. So let's see what this one is. 3 times 8.3145 times 400 and divided by 39.95 and take the square root of it. So I got 15.80 there. And then this one, bring that down there. So now what I want to do is square both sides, right? So that means that takes the square root away from this one and gives us 3 times 8.3145 times 200 divided by molecular weight equals that squared, which is 24.97. Here we go. So now, if we put this one over here in the numerator and this one over here in the denominator, we calculate what the target molecular weight is. Okay, did you see the move? Okay. So I just need to say that one, 8.3145, 200, divide by 7. So our target molecular weight is 19. No. 199. We do that again. That's not right. I was off by a decimal. Okay. It just didn't look right. 15 squared is only 20.
Oh,
Yeah. Okay. Let's try this again. That's better. 19.98 grams per mole. That's our target molecular weight. And then we look at the choices. Right. So what are our choices? Helium, right? That's 4 grams per mole. Can't be that one. Carbon monoxide, that's 12, and 16 is what? 20, 28. Right? That can't be it. HF. So F is 1900 plus 1 is about 20. That's pretty close. See if any others match. HBr. Bromine said 80. That's 81. And fluorine, fluorine is, let's see, it's 19 times 2 is 38. Right. So, has to be this one. Hydrogen fluoride is the gas. We started it. 4 o'clock. Yeah. Okay, we got another half hour. We need to go in the lab. So that was root mean square. Graham's law takes advantage of this relationship. And let's see, here's an example. 112 maybe. Which of the following would have the higher rate of diffusion? That's one way of looking at it. Okay, that's fine. So what does Graham's law say? Which number are we? 112. So we're going to be using Graham's law. We probably need to know what Graham's law says. So the ratio of diffusion rate of one gas to the diffusion rate of another gas is proportional to the square root of the molecular weight of the second gas to the square root of the molecular weight of the first gas. Okay, so back to the question. Which of the following would have a higher rate of diffusion than C2H2? What is C2H2? Any ideas? Probably acetylene. So what are our choices? Our choices are A, nitrogen, B, oxygen, C, chlorine, D, methane, and E, carbon dioxide. Okay, so we're going to have to know the molar masses of all these guys. So that one is 12.01 times 2. Oops. No, there we go. And then 1, actually 2.02, because we have 2 hydrogens. So this one's 2604. Okay. This one is 2802. This one is 32. Chlorine is twice 3545, 7090. Methane, 12.01 plus 4.04, 1605. And CO2 is 12.01 and 32 for the oxygens, 4401. Okay. So, go back to the question. Which of the following would have a higher rate of effusion than C2H2? So the rate of effusion being proportional like this to the inverse. In other words, the heavier the molecule, the slower it moves, right? So even with this formula, this just tells you the relationship. We're not really going to calculate a value. We just know that the relationship is inverse. So which would have a higher effusion rate? Well, anything heavier than that would be slower, right? That's slower. That's slower. That's slower. That's slower. Methane's faster. Okay? I didn't realize how easy it was until I put everything up here and say, oh, simple. Now, if we actually wanted to calculate, what's the ratio of the diffusion rates, we just plug the values in here, and then we get a ratio. And what that ratio would tell you is, well, it could tell you any number of things depending on the experiment. But if we use that glass tube experiment, it would tell you the ratio of the distances traveled. So if we had some way of measuring where these two meet, the H4, where these two meet, they wouldn't meet in the middle. They would probably meet over here somewhere, because this one moves faster than that one. But that ratio would tell you exactly what the ratio of these two distances was. Let's just calculate it. I'm curious. Molecular weight of, let's see. Really doesn't matter as long as we put it in the right place. So let's say this one is acetylene, and this one's methane. So this one is going to be that one, 1605 per root. And this one's going to be 2604. Actually, we can divide this by this and then take the square root. Just 0.79. 0.79. So that's the ratio of this distance traveled to that distance traveled. So 0.79 would be like, this is half, this is 3/4. It would actually be there. Wouldn't it? A lot faster. But then if you know the total length of the tube, then you can find out what measurement, what distance it was. The other way around that is, if you didn't know what the molar mass was of your unknown gas, then you measure this ratio and then back figure it to the unknown. And then that would give you the actual molar mass of the gas, but you wouldn't be able to tell anything without a list to choose from or percent composition data. Then you could do an empirical formula, go the whole 9 yards. One other way of independently determining the molar mass of a compound, so that you can complete the molecular formula. Okay, what else do we need to do? There's got to be some more in here. There are lots more. (138) is actually an example of that, determining the molar mass. Let's see how it reads, if it's really cryptic or straightforward. 138. A sample of unknown gas takes 434 seconds to diffuse through a porous plug at a given temperature. At the same temperature, nitrogen takes 175 to diffuse through the same plug. What's the molar mass of the unknown gas? Oh, okay. So that's simple, that formula again. So diffusion rate can be in really any terms, number of seconds, velocity, whatever. Because it's ratioed, the units cancel anyhow. You just need some measure of how fast it's moving. And that really doesn't matter. Let's see. Well, unless you've got some gnawing problem, I don't see anything else that really jumps out at me. We can retire to the lab. Let's see, what are we doing today? Waters of constitution and hydration. That's a good one. So we're going to take, I think that method, I took the method and crossed out the initial determination where you do a flame test. The reason I did that is because it never works anyway. I can remember doing flame tests in general chemistry, and they never turned out the way we expected. Conditions are just way too variable. Put this back. Let's see. That's not it. This is it. These back in here. There we go. Okay. This shouldn't take too long. We'll be here all day. We'll take a short break and reconvene in the lab. I turned on the fume hoods, hopefully venting out some of that sewer smell. It's coming up from the shower drain vent. There must be a blockage down there somewhere. What we need is to turn on the shower and let it flush. But I need one of those curtains or a big bucket of water that I can pour down just gradually rather than all over the floor. Let's see, let's